Yes, go ahead. Floor is yours. We're shooting for about 10 to 12 minutes.
All right, sure. So hello, everyone. My name is Amir Javid. Today I'm presenting a study, a mechanistic empirical model to predict suction profile in subgrade soils. Let's jump to for interruption. I have probably need. All right, so let's start with some introduction. So subgrade soils are usually unsaturated, and the resilient modulus of subgrade soil is highly dependent on the degree of saturation and the corresponding matrix function. Now, previous study also showed that equilibrium suction has a direct influence on the strength and stiffness of pavement system. So now the next question that came to our mind is how to find the equilibrium suction and moisture regimes. Well, currently there are two popular methods that used for prediction of moisture regime over time and can be classified into two categorical base under state variables. The first one is suction-based methods, and the latter one is seepage analysis. So in this study, we adopted suction-based method to develop a mechanistic empirical model for the moisture regime. All right, to begin with, we first start by collect and evaluate research quality climate data through Oklahoma Mesonet, and then followed by develop an implementable moisture regime prediction model, which comes shortly after this slide. And finally, with that model, we compare it against the predicted values from the finite element seepage analysis. All right, so some formalized theories comes out very soon. But first of all, the seepage change due to the effect of climate, drainage, and site cover is a periodic function of time and can be determined by solving the diffusion equation for following these boundaries. So this is our diffusion equation, and if we have these boundaries, we can find the suction changes. Now, the solution to the diffusion equation solved by linear homogeneous equation, we get this following function. Here we have a u, the suction, which is function of y, the depth, and t, the time. And we can see that here we have ue, which is the equilibrium suction below moisture active zone depth. We can have a unit of pf or kPa. And then we have u naught, which is the amplitude of suction variation. And finally, in our exponential function, we have n as a number of suction cycle per year. Currently, most of the researchers use 1 year here. Of course, we can convert it to seconds. And we have the diffusion coefficient and, of course, the depth. All right. Now that we have the equation, we need to also account for the effect of climate variation. And to do so, we can express an imposing arbitrary state of suction and rewrite our equation as a Fourier series transform, and we get to this bigger equation, which is very long, but here we have, again, we have the y as a depth here, and of course, we have u0, u1, u2, and so on as a Fourier coefficients. These are obtained through Fourier decomposition of surface suction time series that we obtain for each year. So that's how we find those coefficients. We can use solvers, you can use some numerical approach to get it. All right, now I'd like just to get back to previous slide to point out that now that we have most of these inputs in our equation, the only parameter that it's missing is alpha. So we need to find a way to calculate or estimate the alpha as well. All right. So first of all, the diffusion coefficient directly controls the depth of the active moisture zone. That means that a true estimate or reasonable estimate is needed if we want to get the right suction profile. So to do so, what we did, we used the diffusion equation that we have and numerically solve for alpha. To do so, we make a grid of diffusion coefficient range from 10⁻² to 10⁻⁵ square centimeter per second. These values represent the minimum and the maximum nominal values for the diffusion coefficient that we obtained through our literature review of previous studies. Of course, we use Oklahoma Mesonet surface suction measurement, and to numerically solve it, if you recall the equation, the left side was our measured side, is the suction profile, which can be replaced by surface suction. And the right side of the equation, if we plug in our alpha and other values, we can get the fitted suction. The absolute difference of these two changes as we change the alpha. And if the absolute value difference for our study become less than 0.1 decimal places, then we consider that alpha as an estimated alpha for our time and depth of measurement. All right, I think now that we go through lots of formula, everyone wants to see some graphs. So here, first of all, we have the surface suction measurement that we obtained through Oklahoma Mesonet. As you can see, we have two depth of measurement, 5 centimeter and 25 centimeter depth. And we, of course, convert them to PF for demonstration here, and we use PF. These are for Fair Station in Major County, Oklahoma during 2019. And those are average suctions, by the way. All right, now that we have these, surface suction measurement, we follow a procedure and we can get the suction profile at different times. And in this graph, we can see the suction distribution profile for measured suction at 5 centimeter depth at Fair Station in 2019. So the circle ones and blank circles are our measured suction for 4 different months of March, June, September, and October. And using our approach, we are able to find the suction profile with the depth for that time frame. And we also can use our equation to find the boundary conditions using the Fourier series coefficients. So we also get the boundary conditions. Here we can see that after 2 meters, we are reaching our equilibrium suction. All right, so if you repeat this procedure for all 120 Mesonet stations, we can find equilibrium suction for all these stations. And here we see a GIS-based contour map of equilibrium suction in Oklahoma for 2019. We are working on developing more of these maps to better understanding of the variation of suction. It's categorized in 5 different categories here, which shown by different color, and we have those contours to give us more information of the state. All right, now that we have our model, we like to also compare it against the finite element based seepage analysis. So some small formula and theories here. So we have the seepage theory, which is the water flow in I direction here, and then be followed by reference volume. And we also have the, I believe this is the function of the suction is here. This is the soil water characteristic that is come from soil water characteristic curve. The one-dimensional seepage PDE of this equation can be written as this. So we have some observation here. First of all, we have three soil function here. One of them, the first one is Kw here, which is the hydraulic conductivity function. We also have vapor conductivity function for the soil, which is KVD. And finally, we have the MWD2, which is our representative of the suction that we obtained from soil water characteristic curve that we have it on the right. So it's depend on these functions. So we need to have the, these values to solve this 1PD seepage. All right. Beside that, we need to have some weather. Sorry, forgot to silent it. All right. Now that we have the seepage, part of the soil, we also need to have a soil atmospheric interaction model. So we use the Wilson 1919 model equation, which can be written as P stand for precipitation here and equal to AE, which is the actual evaporation. And then we have the NP as a net infiltration. And finally, we have the runoff. Now, the good thing about the seepage here for us was, since Oklahoma, in its previous study, which is maintained for 6 years, they are able to find the soil parameters, Van Gunnington soil parameters. And of course, we have Oklahoma Mesonet to, have the input for the climate boundary conditions at the soil atmospheric model. Now, since we have all those data, we are able to use the seepage analysis. So that's a challenge part in case that someone wants to use the seepage, lots of inputs. So the model that we use the SV flux to do the seepage analysis. This is the one-dimensional model. The surface, it's a 5-meter depth, and of course, on the surface, we have climate boundary conditions. We have those from the mesonets, and at the depth, we have our constant pressure head. So this is the 1D model we use for comparison. And the result, here we have two different graphs that show the result and comparison at two mesonet stations. The left one is the Dora station. The right one is in Atmore, Oklahoma. We do have, two different graphs. The green ones represents our model, the suction-based model here. The purple one is the one that we obtained through the SV flux. The main difference is the SV flux show and capture higher suction values at the surface, but sharply drop to the equilibrium suction. So we can see that it's more to go toward the right side of the dry envelope is when we use the seepage analysis compared to our suction ones. And we have some minor fluctuation at the depth after 3, which we're not expecting. So that's another problem with the finite element solutions. Sometimes they're not converging very well. All right. I think that's all for today. Well, I like to thanks and acknowledge the Tran-SET for providing funds for our research and further improvement of this research study. Thank you guys for listening, and I'm happy to answer any question that you have today.
Great. Thank you very much. We have time for a question. If anyone has anything? All right, hearing nothing, like I said, I do want to encourage you, if you do find that you have questions afterwards or want more information on this work, please feel free to contact the authors directly, or look for their papers when they will be coming out in a while. I'm not sure how long the publication process is, but it'll probably be a few months, and these papers will be published officially through ASCE. But in the meantime, you can always contact one of the authors or presenters for more information. All right, great. Thank you very much.
Thank you, Susan.
All right, moving on. I did mention